Tonight, we're going to unpack one of the strangest confirmed facts in physics. Light has no mass. Zero. Nothing. And yet, the most massive objects in the universe bend it, deflect it, trap it, and in some cases refuse to let it escape at all. That's gravity, doing something Newton's entire framework said was impossible. Gravity turned out to be something else entirely. And light, without any mass at all, bends because of it. By the end of tonight, you're going to understand what gravity actually is, why light has no choice but to follow it, and why answering that question forced us to rebuild our picture of space and time from the ground up. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with what you already know. Gravity pulls things down. You drop a ball, it falls. You throw a ball sideways, it curves toward the ground and eventually lands. This is gravity acting on mass. The ball has mass, Earth has mass, and they attract each other. That's Newton's picture. Simple, elegant, and extraordinarily accurate for almost everything you'll ever encounter in daily life. Isaac Newton published his law of universal gravitation in 1687 in a work called Philosophiae Naturalis Principia Mathematica, which translates roughly as Mathematical Principles of Natural Philosophy. It is considered by many historians of science to be the most important scientific document ever written. The equation at the center of it is clean. Every object with mass attracts every other object with mass. The force between them is proportional to the product of their masses and inversely proportional to the square of the distance between them. Double the distance, the force drops to 1/4. Triple the distance, the force drops to 1/9. This single law explained the orbit of the moon. It explained why planets trace ellipses around the sun. It explained the tides. It explained the slow precession of Earth's rotation axis. It explained the trajectories of comets, falling in from the outer solar system and swinging back out again. Newton's gravity worked so well that it was eventually used to discover planets that no human eye had yet seen. In the 1840s, astronomers noticed that Uranus was drifting slightly off its predicted orbit. The drift was small but consistent. And it was consistent with the gravitational pull of an undiscovered planet beyond Uranus, perturbing its path. Using Newtonian gravity, mathematicians on both sides of the Atlantic independently calculated where this hypothetical planet should be. In September 1846, the astronomer Johann Gottfried Galle pointed a telescope at the predicted location. Neptune was there, right where the math said it would be. That is what an extraordinarily good physical theory looks like. It doesn't just explain what you already know. It predicts things you haven't looked for yet. For over 200 years, Newtonian gravity was the best description of reality anyone had. It was used to design artillery trajectories, predict planetary conjunctions, calculate the paths of spacecraft, and lay the mathematical groundwork for virtually all of classical mechanics. And under this framework, light has an obvious and serious problem. Light has no mass. This is not a matter of uncertainty or approximation. Physicists have tested for photon mass with extraordinary sensitivity. If a photon had any mass at all, even a mass smaller than anything we can directly weigh, it would introduce measurable departures from Maxwell's equations, the equations that govern all electromagnetic phenomena. Different frequencies of light would travel at slightly different speeds. Very low-frequency radio waves would propagate differently from visible light or gamma rays. Long-range electromagnetic fields would look different from what Maxwell's equations predict. None of these effects have been observed. The best experimental upper limit on the photon mass, derived from measurements of the large-scale galactic magnetic field, is less than 10 to the power of negative 54 kilograms. To give that number some context, a single proton has a mass of about 1.7 times 10 to the power of negative 27 kilograms. The upper limit on the photon mass is more than 10 trillion times lighter than a proton. For every practical and fundamental purpose, the photon mass is zero. So under Newton's framework, there is no way for gravity to act on light. Gravity is a force proportional to mass. Light has no mass. Therefore, gravity exerts zero force on light. Zero force means zero acceleration. Zero acceleration means light travels in a straight line through any gravitational field, unaffected, undeflected, indifferent. That was the clean, logical prediction of Newtonian gravity. And it was wrong. The history of how this problem was first approached is illuminating, because Newton's own framework actually generated a prediction for light bending, though built on a flawed foundation. In 1784, an English clergyman, geologist, and natural philosopher named John Michell wrote a paper for the Philosophical Transactions of the Royal Society. Michell was one of the most gifted scientists of the 18th century, though he is largely forgotten today. He correctly described how earthquake waves propagate through the Earth. He was the first person to propose using binary star systems to measure stellar distances. He designed the torsion balance, later used by Henry Cavendish, to measure the gravitational constant and determine the density of the Earth. And in this paper, from 1784, he explored a remarkable implication of Newton's theory applied to light. Newton had proposed, in his Optics, published in 1704, a corpuscular theory of light. In Newton's view, light was a stream of tiny particles, which he called corpuscles, moving through space. If these light corpuscles had mass, Michell reasoned, then gravity should decelerate them when they travel upward, away from a massive object, exactly as gravity decelerates a thrown ball. If a star were massive enough, its gravitational pull would prevent light from escaping. The escape velocity would exceed the maximum speed of light. Michell calculated what such a star would look like. His conclusion: a star with the same density as the Sun, but a radius about 500 times larger, would have an escape velocity equal to the speed of light. No light could leave it. He called these objects dark stars. Not because he imagined anything like the exotic physics we now associate with black holes, simply because they would be dark. No light reaching an observer, gravitationally sealed. Pierre-Simon Laplace, one of the greatest mathematical physicists of his era, reached the same conclusion independently about 12 years later. He included it in his Exposition du Système du Monde, a popular work describing the solar system. Laplace's calculation was equivalent to Michell's. Both were built entirely on the assumption that light consists of massive particles subject to Newtonian gravity. In 1801, a German mathematician and astronomer named Johann Georg von Soldner extended this reasoning. He asked how much starlight would be deflected when it passed close to the surface of the Sun. He treated light corpuscles exactly like cannon shells, computing the deflection of a massive particle grazing the Sun's gravitational field. His answer was 0.84 arc-seconds for a light ray just grazing the Sun's surface. 1 arc-second is 1/3600th of a degree. 0.87 arcseconds is a tiny angle, smaller than the resolution of the human eye. But it is not zero. The problem was experimental. To observe stars very close to the sun in the sky, you need the sun's blinding light blocked. You need a total solar eclipse. And measuring stellar positions during an eclipse with enough precision to detect deflections of less than 1 arcsecond was beyond the technology of 1801. Von Soldner's prediction sat unverified for over a century. The assumption inside it, that light has mass and gravity acts on that mass, seemed reasonable and went unquestioned. Nobody had a better alternative. And so it remained, until physics was rebuilt from the ground up. Albert Einstein published his special theory of relativity in 1905 in a paper titled On the Electrodynamics of Moving Bodies, which appeared in the journal Annalen der Physik. The year 1905 is sometimes called Einstein's miracle year, his annus mirabilis. In that single year, he published 4 papers that each fundamentally advanced physics. One explained Brownian motion, the random jiggling of small particles suspended in fluid, proving that atoms are real. One explained the photoelectric effect, showing that light comes in discrete packets of energy, packets we now call photons, work that earned him the Nobel Prize in 1921. One introduced special relativity, and one derived E equals mc squared as a consequence of special relativity. Einstein was 26 years old. He was working as a patent examiner in Bern, Switzerland. He had no academic position, no laboratory, no students. He was doing physics in his spare time. Special relativity begins from 2 postulates that seem deceptively simple. The first says that the laws of physics look the same for all observers in uniform motion. If you're in a smoothly moving train with the blinds drawn, there's no experiment you can do inside the train that tells you whether you're moving or stationary. Physics works the same either way. The second postulate is more radical. It says the speed of light in a vacuum is the same for all such observers, regardless of the motion of either the observer or the light source. This contradicts ordinary common sense about how velocities combine. If someone throws a ball at 50 kilometers per hour from a train moving at 100 kilometers per hour, the ball's speed relative to a stationary observer is 150 kilometers per hour. Velocities add. But light doesn't work this way. If someone fires a laser from a spacecraft moving at 90% the speed of light, the laser beam doesn't travel at 190% the speed of light relative to a stationary observer. It travels at exactly 100% the speed of light, 300,000 kilometers per second. Every observer in every state of uniform motion measures exactly the same speed for the same beam of light. This bizarre fact was confirmed experimentally by the Michelson-Morley experiment of 1887, which measured the speed of light along Earth's direction of motion and perpendicular to it, and found no difference despite the Earth's orbital velocity of 30 kilometers per second. The speed of light is the same in all directions for all observers. But taking this seriously requires that time itself be relative. Consider what happens if 2 observers moving relative to each other both measure the speed of the same light beam and both get the same answer. For that to work, they must be measuring different amounts of space and time. Their clocks must tick at different rates. Their rulers must be different lengths. And their measurements of which events are simultaneous must disagree. All of this follows logically from the constancy of the speed of light. And all of it is real. Moving clocks genuinely tick more slowly. Moving objects genuinely contract along their direction of motion. Simultaneity genuinely depends on the observer's state of motion. These are not measurement artifacts or optical illusions. They are features of the fundamental structure of space-time. Moving atomic clocks carried on aircraft have been compared to stationary clocks and found to run slower by exactly the amount special relativity predicts. Particles at high speed in accelerators survive much longer than stationary versions of the same particles because their internal processes are time-dilated. The effects are real, measured, confirmed. From this framework emerged E equals mc squared. Energy equals mass times the speed of light squared. The speed of light squared is about 90 billion square kilometers per second squared. That is an enormous number. Multiply any mass by it, and you get the energy locked inside that mass. The implication runs both ways. Mass and energy are equivalent. Mass is a form of energy. Energy has an associated mass. A compressed spring has slightly more mass than an uncompressed one. A hot object has slightly more mass than a cold one. A photon, despite having no rest mass, carries energy, and energy has mass equivalence. A photon has an effective mass by virtue of its energy, not a rest mass. But a gravitational presence proportional to its energy, this was a hint. But special relativity couldn't describe gravity. It described objects moving through flat, undistorted spacetime. It had nothing to say about what happens when spacetime itself is curved by the presence of mass. That required 10 more years of work. The work that produced general relativity. Between 1905 and 1915, Einstein worked on extending his relativity to include gravity. He described this effort later as a struggle of unprecedented difficulty, more demanding than anything he had previously faced. The first key insight arrived in 1907. Einstein later called it the happiest thought of his life. He imagined a person in free fall, falling from a building. During the fall, the person is weightless. Objects released alongside the falling person don't accelerate relative to them. Everything is in free fall, together. From the falling person's perspective, gravity seems to have disappeared. Einstein recognized something profound in this. The local effects of gravity can be entirely eliminated by going into free fall. And the reverse is also true. A person in an accelerating rocket with no gravitational field present experiences effects indistinguishable from being in a gravitational field. The floor pushes up against their feet. Objects fall toward the floor when released. Light, emitted horizontally, curves toward the floor. There is no local experiment that distinguishes being in a gravitational field from being in an accelerating reference frame. This is the equivalence principle. Gravity and acceleration are locally equivalent. Einstein elevated this observation to a fundamental principle and derived immediate consequences. If gravity and acceleration are equivalent, and if an accelerating observer sees light deflect, then gravity must also deflect light. He calculated how much, using the equivalence principle alone, and published a result in 1911. His prediction, starlight grazing the sun, would be deflected by about 0.83 arcseconds. This is essentially the same as von Soldner's Newtonian answer. Not because they made the same assumptions, but because the equivalence principle, correctly applied, captures the same effect that Newtonian gravity captures for this calculation. Einstein knew, though, that this couldn't be the whole story. The equivalence principle works locally, in small regions of space-time over short times. A complete theory of gravity, one describing curved space-time across large regions and near arbitrary mass distributions, required more structure. It required a mathematical framework for describing curved geometry in 4 dimensions. And Einstein didn't know that mathematics well enough. He turned to his friend, Marcel Grossmann, a mathematics professor at the Swiss Federal Institute of Technology in Zurich. Grossmann pointed him to the work of Bernhard Riemann. Riemann, in the 1850s, had developed a comprehensive mathematical framework for curved spaces of arbitrary dimension, Riemannian geometry. The mathematical tools he developed, tensors, covariant derivatives, the curvature tensor named after him, were exactly what Einstein needed. Riemann had invented this mathematics for purely abstract reasons. He was exploring the logical foundations of geometry itself. He had no physical application in mind. He could not have imagined that 60 years later, his abstract framework would become the language in which the geometry of space and time is written. Einstein had to master all of it. He collaborated with Grossmann. He corresponded frantically with mathematicians and physicists across Europe. He made mistakes, published incorrect intermediate results, and had to retract them. He went down wrong paths and backtracked. And in November of 1915, across 4 papers published at the Prussian Academy of Sciences in Berlin, on 4 consecutive Thursdays, general relativity emerged complete. The final paper, on November 25, 1915, contained the field equations in their final form. They relate the curvature of spacetime, expressed through the Einstein tensor built from Riemann's curvature tensors, to the content of spacetime, expressed through the stress-energy tensor. In essence, matter and energy tells spacetime how to curve. Curved spacetime tells matter and energy how to move. That is gravity, not a force. Not action at a distance. Not a mysterious pull across empty space. Geometry. The conceptual shift that general relativity demands is difficult to fully absorb because it requires replacing a picture of gravity that works so well in everyday life with something far more abstract and far more fundamental. In Newton's universe, space is a fixed, flat, 3-dimensional stage on which events take place. Time flows uniformly and independently of everything, the same everywhere, the same for everyone. Gravity is a force that objects exert on each other across space, instantaneously, proportional to their masses, and inversely, proportional to the square of their separation. This picture is intuitive. It matches our everyday experience. It makes accurate predictions for everything we deal with in ordinary life. But it is wrong about what gravity actually is. In Einstein's universe, space and time are not separate and fixed. They are woven together into a single 4-dimensional fabric called space-time. And space-time is not passive. It is dynamic. It responds to the presence of mass and energy by curving. The curvature of space-time is what we call gravity. Objects don't move through flat space under the influence of a gravitational force. They move through curved space-time, following the straightest possible paths through whatever geometry exists in their vicinity. These paths are called geodesics. In flat space-time, with no mass nearby, geodesics are simple. An object at rest stays at rest. An object in motion continues at the same speed in the same direction. Newton's first law, expressed geometrically. Near a massive object, space-time curves. Geodesics curve with it. An object following a geodesic near a massive body appears, to a distant observer, to accelerate toward the mass, which is what we call gravitational attraction. The Earth doesn't pull the Moon toward it. The Earth's mass curves the spacetime around it. The Moon follows a geodesic through that curved spacetime. The geodesic is an ellipse, an orbit. This is not a metaphor or an analogy. This is what is actually happening. The curvature of spacetime is as real as the curvature of a ball. You can measure it. You can calculate its effects. You can observe them directly. And now, the critical point for light. In Newton's framework, the question was whether gravity could act on something with no mass. The answer was no. Gravity is proportional to mass. No mass, no gravity. Massless light should travel in straight lines through any gravitational field, completely unaffected. In Einstein's framework, the question is completely different. The question is not what gravity acts on. The question is, what follows geodesics? And the answer is everything. Everything that exists in spacetime follows geodesics. Every massive particle, every massless photon, every field, every excitation of every quantum field, all of it follows the geodesics of the spacetime it inhabits. This is not a special rule for certain kinds of things. It is the universal rule for everything. Light bends near massive objects, not because gravity reaches out and pulls on the photon's mass. Light has no mass to pull on. Light bends because spacetime is curved near massive objects, and light, following geodesics, follows the curvature. A photon, grazing the surface of the sun, travels in a geodesic. That geodesic bends around the sun because the sun's mass has curved the surrounding spacetime. From outside, watching the photon's path, you see a curved trajectory. From the photon's perspective, so to speak, it is following the straightest available path through a curved space. The curvature is in the space, not in the motion. And the amount of curvature felt by the photon is different from what Newton's theory predicts. Newton's theory has no spatial curvature. It only modifies time. Einstein's theory modifies both space and time. And for light, both modifications matter. The difference between Newton's prediction and Einstein's prediction for the deflection of light comes entirely from this missing spatial curvature. Von Soldner's Newtonian calculation gave about 0.87 arc-seconds. Einstein's general relativistic calculation gives 1.75 arc-seconds, exactly twice. The factor of 2 is not approximate. It is exact. And it comes from the full geometry of curved spacetime. Near a massive body, spacetime is curved in two distinct ways. First, time is dilated. Clocks run more slowly closer to the mass. The rate at which time passes varies with position in the gravitational field. This variation in the rate of time passage changes the apparent direction of a light ray, because the wavefronts of the light are advancing at slightly different rates at different distances from the mass. The effect of this time dilation on the light ray's apparent path produces a deflection of about 0.87 arc-seconds. This is the contribution that Newtonian gravity captures. Or more precisely, it's what the equivalence principle captures. The principle that gravity locally mimics acceleration. Acceleration causes time dilation in special relativity. By equivalence, so does gravity. And that time dilation deflects light. Second, space itself is curved near the mass. The spatial geometry near a massive body is non-Euclidean. Distances measured near the mass are different from what flat Euclidean geometry would predict. A ruler near the Sun is slightly longer than an identical ruler far from the Sun. Not because anything happened to the ruler, because the space it occupies has a different geometry. This spatial curvature also deflects the light ray. It contributes an additional deflection of about 0.87 arcseconds, the same amount as the time contribution. They add together. Total deflection, 1.75 arcseconds, twice the Newtonian answer. Newton's theory has no spatial curvature. Space, in Newton's framework, is flat and Euclidean always. Only time is affected by gravity, and even then, Newton didn't know that. The time dilation of gravity wasn't part of Newtonian mechanics. Von Soldner's calculation implicitly captured it by treating light as particles with momentum falling in a gravitational field. But neither Newton nor von Soldner had any concept of spatial curvature. That was purely Einstein's contribution, and it doubled the answer. This means these two theories make predictions that differ by a factor of 2, and both predictions are testable against experiment. That test came 4 years after general relativity was published. Arthur Eddington was a British astrophysicist at Cambridge University and one of the first scientists in the English-speaking world to fully understand and embrace Einstein's general relativity. During the First World War, direct scientific communication between Britain and Germany was cut off. Einstein's papers reached Eddington through colleagues in the Netherlands, which maintained scientific links with both sides. Eddington studied the papers carefully. He became convinced that general relativity was correct. He understood that the eclipse of May 29, 1919, would provide the key experimental test. During a total solar eclipse, the moon blocks the sun completely for a few minutes. The sky darkens to twilight. Stars near the sun in the sky, which are normally invisible in the solar glare, become photographable. By comparing photographs of these stars taken during the eclipse to reference photographs of the same stars taken months later when the sun was elsewhere in the sky, you could measure how much the sun had shifted the apparent positions of the stars. Eddington organized 2 expeditions with support from the Royal Astronomical Society and the Royal Society. One team, led by Frank Watson Dyson and Andrew Crommelin, traveled to Sobral in the state of Ceará in northeastern Brazil. The second team, led by Eddington himself, traveled to the island of Príncipe off the west coast of Africa, in what is now the nation of São Tomé and Príncipe. Both locations lay in the path of totality. The weather at Príncipe was worrying. Clouds covered the sky for most of the eclipse morning. Eddington watched anxiously. In the final minutes of totality, the sky partially cleared. His team captured a handful of usable photographs through gaps in the clouds. Not many, but some. The Sobral team had generally better weather, but faced a technical problem. They brought 2 telescopes. The smaller one, a 4-inch astrographic refractor, performed well and produced sharp images. The larger one, a 13-inch astrographic telescope, suffered from thermal problems. The heat of the eclipse day caused the telescope's mirror to expand and shift focus. The plates from the large telescope were blurred and yielded poor results. The analysis of the eclipse photographs took months. The plates were carefully measured at the Royal Observatory in Greenwich. and by Eddington's group at Cambridge. The positions of stars on the eclipse plates were compared to their positions on the reference plates. The differences in apparent position, the shift caused by the sun's gravity bending the starlight, were measured. The results, when compiled, were consistent with Einstein's prediction of 1.75 arcseconds. Not with Newton's 0.87. Not with zero. With Einstein. The announcement came at a famous joint meeting of the Royal Society and the Royal Astronomical Society on November 6, 1919, at Burlington House in London. The Astronomer Royal, Frank Watson Dyson, presented the results. J. Thomson, who had discovered the electron, presided. He said that this was one of the greatest results obtained in connection with the theory of gravitation since Newton's day. He compared the result in importance to Newton's original discovery. The following morning, the Times of London ran a front-page headline that has become famous in the history of science. Revolution in Science. New theory of the universe. Newtonian ideas overthrown. Einstein became the most famous scientist in the world. Not just famous to other scientists. Famous everywhere. Newspaper front pages. Magazine covers. Public lectures that drew thousands. His name synonymous with genius across all languages. Not because he had invented a technology, not because he had built a machine, but because he had figured out something true about the universe that no one had known before, and the universe had confirmed it. The photon, with no mass, had bent by the amount curved spacetime predicted. The geometry was doing the work, and Newton's picture, while extraordinarily useful, had been incomplete. Now, the Eddington result has been scrutinized by historians of science, and some of the criticism is fair. The measurements were difficult. The uncertainties were substantial. The Principe data were limited by clouds. The data from the Large Sobral Telescope were largely unusable. Eddington was a committed supporter of Einstein's theory, raising questions about whether unconscious bias might have influenced his interpretation of ambiguous data. Later, reanalyses of the original photographic plates have yielded mixed assessments. Some analysts found the original data less decisive than Eddington and Dyson presented. These are legitimate concerns in the history of science, but they are irrelevant to the physics. In the century, since 1919, the deflection of light by the sun has been measured with a precision that makes the original eclipse observations look like rough sketches. Radio astronomy transformed the field. Radio waves obey the same physics as visible light. They are photons at much longer wavelengths, following the same geodesics through curved spacetime. Radio observatories can observe near the sun during daytime without waiting for an eclipse. As the Earth orbits the sun through the year, different distant radio sources pass near the sun from our perspective. Each time a radio source moves close to the sun in the sky, its light must traverse the curved spacetime near the sun and is correspondingly deflected. By tracking the apparent positions of these sources throughout the year, measuring how their positions shift when their light passes near the sun versus when the sun is far away, you can measure the deflection with great precision. The Very Long Baseline Array, a network of 10 radio telescope dishes distributed from Hawaii to the US Virgin Islands, achieves angular resolutions of tens of micro-arcseconds through very long baseline interferometry. It combines signals from all its dishes, synchronized by hydrogen mesa atomic clocks, to achieve resolution equivalent to a telescope thousands of kilometers across. 1 microarcsecond is 1/1,000,000th of an arcsecond. Eddington's measurements had uncertainties of several tenths of an arcsecond. The Very Long Baseline Array achieves precision roughly 10,000 times better. Radio measurements of gravitational deflection confirm Einstein's prediction to better than 0.02%. This is not an approximate confirmation, not a qualitative agreement. It is a quantitative match to within 0.02%. The theory is right. Light bends by exactly the amount curved spacetime predicts. Every time. Not because gravity is acting on the photon's mass, because the spacetime the photon moves through is curved by the nearby mass. The bending of light near individual stars produces angles of roughly 1 or 2 arcseconds. Small. Precise instruments are required to see it. But the universe contains objects far more massive than individual stars. Galaxy clusters contain the mass of hundreds of billions to trillions of suns, sometimes more. When that much mass occupies a region of space, the curvature of spacetime it produces is not subtle. It produces effects visible to the naked eye in telescope photographs. The effect of a massive foreground object bending the light from a more distant background source is called gravitational lensing. The geometry is simple to describe. A distant source emits light in all directions. A massive object sits between the source and the observer. Light from the source that would have passed the observer on the left side of the lens is bent toward the observer. Light that would have passed on the right side is also bent toward the observer. Light passing above and below is similarly redirected. The lens concentrates light from the source that would otherwise have missed the observer. If the alignment is perfect, with source, lens, and observer exactly collinear, light is concentrated from all sides equally. It forms a ring, a complete circle of light surrounding the lens. Einstein worked out the mathematics of this in 1936 in a short paper published in Science at the request of R.W. Mandel, an amateur scientist who had written to Einstein to discuss the idea. Einstein calculated the angular size of the ring as a function of the masses and distances involved. He found it would be tiny for individual stars as lenses, roughly a milliarcsecond. He concluded that there was no hope of observing such an effect, and described the paper as of no great value. He was wrong about the observational relevance. What Einstein didn't anticipate was that entire galaxies could serve as lenses. For a galaxy with the mass of 1 trillion suns as the lens, the Einstein ring radius is not milliarcseconds. It is arcseconds or more, visible in ordinary telescope images. And the probability of alignment is not negligible when the lens is a large extended object and background sources are numerous. The first gravitational lens was discovered in 1979. Dennis Walsh, an English astronomer working at Jodrell Bank, Robert Carswell, a New Zealander at Cambridge, and Ray Wayman, an American at Steward Observatory in Arizona, were conducting a systematic survey of quasars. Quasars are the extraordinarily luminous cores of distant active galaxies, powered by supermassive black holes, consuming gas at high rates. During the survey, the three noticed 2 quasars separated by only 6 arcseconds on the sky. Close proximity alone was not remarkable, but their spectra were identical. Both had the same redshift. Both showed the same pattern of absorption lines at the same wavelengths, indicating their light had passed through the same intervening gas clouds. 2 independent quasars with identical spectra is essentially impossible by chance. 2 images of the same quasar is the only explanation. The team identified the lensing galaxy between the two images. A foreground galaxy sitting almost exactly between Earth and the quasar, bending the quasar's light into two beams arriving from slightly different directions, producing two images of one source. The quasar was catalogued as Q0957 plus 561. It became known informally as the twin quasar. Discovery. Announced in Nature in May 1979, it was the first confirmed gravitational lens. Since then, thousands have been found. They appear in every deep survey of the sky. Any photograph of a massive galaxy cluster shows background galaxies stretched into arcs, curving around the cluster. Some background galaxies appear as multiple images. Some are split into 3 or 4 or 5 images by the complex mass distribution of the lensing cluster. Some are magnified to many times their true apparent brightness, making them visible when they would otherwise be too faint for even the largest telescopes. The Einstein ring that Einstein himself predicted and dismissed as unobservable has been seen many times. When the alignment is close enough to perfect, the background source appears as a nearly complete ring surrounding the foreground lens. One of the most visually striking examples is called the horseshoe Einstein ring. The foreground object is a galaxy called LRG 3757, a large red elliptical galaxy. Red elliptical galaxies are old galaxies. Their stellar populations dominated by cool, old, red stars. They are among the most massive galaxies known, the products of billions of years of galactic mergers. LRG 3757 sits about 4.6 billion light-years from Earth. Behind it, nearly perfectly aligned, is a blue star-forming galaxy roughly 11 billion light-years away. Blue star-forming galaxies are blue because they are producing new stars rapidly. The hottest, most massive, brightest of those new stars dominate the galaxy's light. Hot, massive stars emit blue light. The alignment between LRG 3757 and the background blue galaxy is close to perfect. The background galaxy's light wraps almost entirely around the foreground galaxy. In Hubble Space Telescope images, the result is a vivid blue arc, nearly a complete ring, surrounding the orange-red foreground galaxy. The contrast in color makes it visually unmistakable. Orange galaxy, surrounded by a blue ring of light. The blue light departed the background galaxy 11 billion years ago. When it left, the foreground galaxy through which it would be lensed did not yet exist. The red elliptical galaxy formed billions of years later, out of the mergers of smaller galaxies. The lensed light predates the lens by billions of years. A ring of ancient light, bent by the gravity of a galaxy that formed billions of years after the light began its journey, delivered to human telescopes as a glowing arc in a digital image. That is what happens when you take the geometry of space-time seriously. Now, take the reasoning to the extreme case. We've been discussing light bending by small angles near stars and dramatically near galaxy clusters. But what happens when mass is concentrated so densely that the curvature of space-time becomes not just dramatic but total? What happens when there are no outward geodesics? This is where black holes come in. Michel and Laplace describe dark stars using Newtonian reasoning. Escape velocity exceeds the speed of light. Light can't escape. But their picture rested on wrong assumptions. Light was treated as having mass and being slowed by gravity. In general relativity, the situation is fundamentally different. Near a black hole, the curvature of space-time becomes so severe that all future-pointing geodesics lead inward. Not that light is pulled backward. Not that gravity is slowing the photon and preventing it from climbing out. Rather, the geometry of space-time itself has become such that there is no outward direction. From inside the event horizon, every path through space-time, no matter what direction you start in, leads to smaller radius. There is no geodesic leading outward. The exit doesn't exist as a geometrical feature. You cannot fight your way out by going faster. There is no faster. Every direction is inward. This was first worked out mathematically by Carl Schwarzschild. Schwarzschild was an extraordinary physicist and astronomer who had been conscripted into the German army during the First World War. He served first on the Western Front, then was transferred to the Eastern Front, where he was serving as an artillery officer when Einstein published his general relativity papers in November 1915. Schwarzschild received copies of Einstein's papers and, in the months before he contracted the illness that would take his life in May 1916, worked out an exact solution to Einstein's field equations. Not an approximate solution, an exact one. The Schwarzschild solution describes the space-time geometry outside a perfectly spherical, non-rotating mass. It is still used today as the basis for calculating the behavior of light near ordinary stars and near the simplest type of black hole. The solution contains a particular radius, now called the Schwarzschild radius, at which the mathematical description of the geometry changes qualitatively. For any mass, this radius has a definite value. For Earth, the Schwarzschild radius is about 9 millimeters. For the Sun, it's about 3 kilometers. For a 1 kilogram rock, it's about 1.5 times 10 to the power of negative 27 meters, far smaller than an atomic nucleus. These objects are vastly larger than their Schwarzschild radii. Earth is 8,000 kilometers across. The Sun is nearly 1.4 million kilometers across. The Schwarzschild radius is deep inside them, where the exterior Schwarzschild solution doesn't apply. But stars that are much more massive than the Sun, at the end of their lives, can collapse. If the remaining mass collapses within its Schwarzschild radius, the geometry of the exterior spacetime develops an event horizon, a black hole. Outside the event horizon, light is severely deflected. At a specific radius called the photon sphere, located at 1.5 times the Schwarzschild radius. The curvature of spacetime is exactly strong enough for a photon to travel in a perfect circle around the black hole, not escaping, not falling in, orbiting indefinitely, at least in principle. In practice, the circular photon orbit is unstable. A photon at precisely this radius, given any small perturbation, either spirals inward toward the singularity or spirals outward and escapes. The photon sphere is a knife edge. Photons passing just outside the photon sphere can make partial orbits around the black hole before escaping. Some are deflected by 90 degrees, some by 180 degrees. Some, approaching the photon sphere asymptotically, make multiple complete orbits before escaping. The result is a complex lensing structure. From a distant observer, a black hole appears as a dark shadow surrounded by a bright ring. The dark shadow is the region from which no photons can escape. The bright ring is formed by photons that have been bent enough to redirect toward the observer, including some that have partially orbited the photon sphere. Inside the primary bright ring, secondary and tertiary subrings correspond to photons that made additional orbits. They are dimmer and narrower, with the spacing between them decreasing exponentially as you go inward. All of this was derived theoretically from the mathematics of curved spacetime, from geodesics in the Schwarzschild metric and the Kerr metric for rotating black holes, decades before anyone thought a direct image was achievable. And in April 2019, it was photographed. The Event Horizon Telescope is a network of radio observatories distributed across the planet. The Atacama Large Millimeter and Sub-Millimeter Array in Chile, the South Pole Telescope in Antarctica, the Sub-Millimeter Array in Hawaii, the James Clerk Maxwell Telescope in Hawaii, the Institut de Radioastronomie Millimétrique 30-meter telescope in Spain, the Institut de Radioastronomie Millimétrique Plateau de Bure interferometer in France, the Large Millimeter Telescope in Mexico, the Sub-Millimeter Telescope in Arizona. All of them observing simultaneously, synchronized by hydrogen maser atomic clocks, recording data on high-density disk arrays. The data were then correlated using very long baseline interferometry, combining the signals to achieve an angular resolution equivalent to a telescope as large as the separation between the most distant dishes. The target was Messier 87, a giant elliptical galaxy about 55 million light-years away in the Virgo cluster. At its center is a supermassive black hole with a mass of approximately 6.5 billion solar masses. The Schwarzschild radius of such a mass is about 19 billion kilometers. The photon sphere sits at about 29 billion kilometers from the center. From Earth, the shadow subtends an angle of about 42 micro-arc seconds. The image released on April 10, 2019, showed a dark central region surrounded by an asymmetric bright ring. The asymmetry, a brighter southern edge and dimmer northern edge, results from the black hole's rotation. Rotating black holes drag the surrounding spacetime in the direction of their rotation through the frame-dragging effect. The material in the accretion disk orbiting the black hole moves faster on the side, approaching the observer, and the brightening from this motion is what creates the asymmetry. The specific brightness ratio matches general relativistic models of the accretion disk around a black hole with the estimated mass and spin of Messier 87's central object. 3 years later, in May 2022, the collaboration released an image of Sagittarius A, the black hole at the center of our own Milky Way. Sagittarius A has a mass of about 4 million solar masses. It sits about 26,000 light-years from Earth. Its Schwarzschild radius is about 12 million kilometers. Despite being much closer than the Messier 87 black hole, Sagittarius A is harder to image because gas near it moves much faster, completing orbits in minutes rather than days. The image of Sagittarius A was blurred by this variability during the hours-long observation. Sophisticated computational techniques were needed to reconstruct the underlying structure from data that had blurred during the observation. The resulting image again showed a dark shadow surrounded by a bright ring. Same structure, same physics, same geometry. Two black holes, photographed directly, one 55 million light-years away, one 26,000 light-years away, both confirming that light follows geodesics through curved space-time in precisely the way general relativity predicts. There is a subtler consequence of light moving through curved space-time that is equally real and directly affects everyday technology. If spacetime near a massive object is curved, and light follows the geodesics of that curved spacetime, then a light signal traveling through a region of curved spacetime doesn't just change direction. It also takes longer to arrive than it would if the space were flat. The geodesic path through curved spacetime is longer than the equivalent straight-line path through flat space. Light moves at the speed of light locally, but there is more spacetime to traverse. The signal arrives later. This effect was predicted by Erwin Shapiro in 1964, in a paper published in Physical Review Letters. Shapiro was thinking about the possibilities of planetary radar astronomy. Scientists had recently developed the capability to bounce radar signals off the surfaces of Venus and Mercury and measure the round-trip travel time. Shapiro recognized that a signal path passing near the Sun would be delayed by the Sun's gravitational field. The curvature of spacetime around the Sun makes the effective path longer than flat space geometry would indicate. For a signal just grazing the Sun, the extra delay would be about 200 microseconds. He proposed testing this by timing radar signals to Venus and Mercury at different times of year, including when the signals pass closest to the Sun. The first experiments were done between 1966 and 1968. Radar beams were bounced off the surfaces of Venus and Mercury near Superior Conjunction, when the planets were on the far side of the Sun and the radar signals had to pass through the region of strongly curved spacetime near the Sun. The measured delays matched the predictions of general relativity. The Shapiro delay was real. The most precise measurement of the Shapiro delay was done in 2002 using the Cassini spacecraft on its way to Saturn. As Cassini passed through Superior Conjunction, radio signals between Earth and the spacecraft had to pass close to the Sun. The delay was measured as a function of the angle between the signal path and the Sun. The result matched general relativity to within 1 part in 100,000. This is one of the most precise confirmations of general relativity ever achieved. And it is not merely academic. GPS satellites orbit Earth at an altitude of about 20,000 kilometers. At that altitude, the gravitational potential is weaker than at Earth's surface. Space-time is less curved. Clocks in regions of weaker space-time curvature tick faster than clocks in regions of stronger curvature. The GPS satellite clocks gain about 45 microseconds per day relative to ground clocks due to this gravitational time dilation. There is also a special relativistic effect. The satellites move at about 3.9 kilometers per second relative to ground observers. Clocks on moving objects tick more slowly than clocks at rest, as described by special relativity. This velocity effect causes the satellite clocks to lose about 7 microseconds per day. The two effects partially cancel. The net result is that the satellite clocks gain about 38 microseconds per day relative to ground clocks. GPS works by comparing the arrival times of signals from multiple satellites. The system calculates your position from the differences in signal timing. If the relativistic corrections were not applied, the timing errors would accumulate. At the speed of light, 38 microseconds corresponds to about 11 kilometers. After 1 day of uncorrected operation, GPS position errors would exceed 11 kilometers. After a week, they would be about 75 kilometers. After a month, several hundred kilometers. The navigation system would be useless. GPS engineers knew this before the first satellite was launched. They built relativistic corrections into the system. The satellite clocks are deliberately set to tick at a slightly different rate before launch, so that once in orbit, the combination of gravitational and velocity effects brings them into synchrony with ground clocks. The correction works. GPS positions are accurate to a few meters. Every time you navigate with your phone, every time a pilot uses satellite guidance, every time a container ship crosses an ocean using GPS positioning, every time precision agriculture uses GPS-guided equipment to plant within centimeters of the intended position, the correction that makes it work is a correction for general relativity, the same physics that explains why gravity bends light. The geometry of space-time is not an academic abstraction. It is woven into the infrastructure of modern civilization. Return to the equation. E equals mc squared. Energy equals mass times the speed of light squared. This equivalence means that mass and energy are not fundamentally different things. They are two aspects of the same thing. Mass is a form of energy. Energy has an associated inertia, an effective mass. In general relativity, what curves space-time is not just mass. It is the full stress-energy tensor, which includes energy, momentum, pressure, stress, and mass. Any form of energy curves space-time. A region of space filled with hot plasma has more energy than the same region filled with cool gas. The hot plasma curves space-time more strongly. A region filled with photons, with light, has energy. That energy curves space-time. In the very early universe, shortly after the Big Bang, the temperature was so high and the density of radiation was so great that it was radiation, photons, light, that dominated the energy content. Massless photons were the primary source of gravitational effects. The expansion of the early universe was driven primarily by the gravity of radiation. This is not a minor correction to the usual picture. It is the dominant effect in the first few tens of thousands of years of cosmic history. The gravitational influence of massless photons shaped the large-scale structure of the universe. And at the individual particle level, two photons traveling toward each other do gravitationally attract. The gravitational interaction between two antiparallel photon beams is not zero. It is tiny, utterly unmeasurable for any beams we could produce. But it is there. It follows from the stress-energy tensor. Photons contribute to it. Therefore, photons exert gravitational effects. Light gravitates, not through mass, through energy. And energy is mass by E equals mc squared. So light does have an effective mass in the sense of gravitational mass, just not a rest mass. The distinction that matters for gravity is not rest mass. The distinction that matters for geometry is the stress-energy tensor. And light contributes to the stress-energy tensor. So, light curves space-time, and light responds to curved space-time. The original Newtonian picture, in which gravity acts on mass and massless light is immune, was wrong in the deepest sense. Not just numerically wrong in its prediction, conceptually wrong about what gravity is. Gravity does not act on mass. Gravity is the curvature of space-time. Curvature acts on everything in space-time, including light. Now there is something at the frontier of physics that the story requires mentioning, because it is honest to say where our understanding ends and the open questions begin. General relativity is extraordinarily successful. Its predictions have been confirmed to extraordinary precision in every regime where they can be tested. Gravitational wave astronomy has provided yet another confirmation. Gravitational waves are ripples in the fabric of space-time itself, produced by the acceleration of massive objects. Merging binary black holes and neutron stars produce the strongest gravitational waves detectable with current technology. Einstein predicted gravitational waves in 1916 as a consequence of general relativity. He calculated that accelerating masses should produce ripples in space-time that propagate outward at the speed of light. He was uncertain whether they were real physical effects or mathematical artifacts. They are real. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time on September 14, 2015. The signal came from two black holes, each about 30 solar masses, spiraling together and merging roughly 1.3 billion light-years away. The merger lasted a fraction of a second. In that brief interval, the colliding black holes released more energy as gravitational waves than the entire observable universe emits as light. The signal, when it reached Earth, distorted the LIGO detectors by less than 1,000th the diameter of a proton. LIGO measured it anyway. The shape of the signal, the way the frequency increased and then cut off as the black holes merged, matched the predictions of general relativity to extraordinary precision. The LIGO collaboration has since detected dozens of merging compact objects. The scientists who led LIGO's development, Rainer Weiss, Barry Barish, and Kip Thorne, received the Nobel Prize in Physics in 2017. Gravitational wave astronomy has become an entirely new way of observing the universe, one that doesn't rely on light at all. It relies on ripples in the geometry of space-time, on the same space-time whose curvature explains why light bends. But, despite all these successes, general relativity is not complete. It is incompatible with quantum mechanics. Quantum mechanics is the most precisely tested theory in the history of science. Its predictions match experiment to more than 10 decimal places in some cases. But it describes reality in a way that is fundamentally incompatible with the smooth, continuous space-time of general relativity. Quantum mechanics is built on discreteness and probability. Physical quantities take definite values only when measured. Between measurements, they exist in superpositions. The positions and momenta of particles are fundamentally uncertain. Heisenberg's uncertainty principle is not a statement about the limits of measurement technology. It is a statement about nature. General relativity describes smooth, continuous space-time. Space-time in general relativity is a precisely defined mathematical manifold. Every point has definite coordinates. Every region has definite curvature. Physical quantities like the metric tensor are smooth functions. When you try to apply both theories simultaneously, in conditions where both must apply, the equations break down. At the center of a black hole, general relativity predicts infinite density, a singularity. Quantum effects should prevent the density from actually becoming infinite, but we don't have a theory to describe what happens. In the first tiny fraction of a second after the Big Bang, the universe was small enough and dense enough and hot enough that quantum effects on space-time itself must have been important. But we can't describe that era. Not because we lack data, but because the theory of quantum gravity that would describe it does not yet exist. String theory is the most developed candidate for a theory of quantum gravity. Loop quantum gravity is another. There are others. None has produced a prediction that has been confirmed by experiment. None is complete. The search for quantum gravity is one of the central unsolved problems in fundamental physics. And without quantum gravity, our understanding of how light interacts with extreme curved spacetime is incomplete. For practical purposes, for every situation where we can do experiments, general relativity works. But at the Planck scale, 10 to the power of -35 meters, the scales at which quantum effects on spacetime become important, our description breaks down. The full story of how gravity bends light has not yet been written. With all of that established, step back and see what the complete picture looks like. The question was, why does gravity bend light if light has no mass? The question assumes gravity acts on mass. That assumption is wrong. Gravity is the curvature of spacetime. Everything that moves through spacetime follows the geodesics of that curved spacetime, including massless photons. Mass and energy curve spacetime. Light responds to that curvature by following its geodesics. Mass is irrelevant to whether light bends. What matters is the geometry. When you replace the Newtonian picture with the correct picture, the bending of light stops being puzzling. It becomes inevitable. The only thing that needs explaining is why it took until 1915 to understand what gravity actually is. And once the correct understanding was in place, the consequences unfolded rapidly. The deflection of starlight by the sun, confirmed in 1919, established that general relativity was correct. Gravitational lensing of galaxies, discovered in 1979, opened a new window on the universe. The shadows of black holes, photographed in 2019 and 2022, confirmed the most extreme predictions of curved spacetime geometry. The Shapiro delay, measured to 1 part in 100,000, confirmed that curved spacetime lengthens the path of light signals. And GPS, corrected for relativistic effects every day, proved that this abstract geometric theory has immediate practical consequences. All of it connected. All of it following from the same principle: mass and energy curve spacetime. Light follows geodesics through curved spacetime. Therefore, gravity bends light. Gravitational lensing, beyond being a spectacular confirmation of general relativity, has become one of the most important tools in modern astrophysics. And one of the most important things it has revealed is the existence and distribution of dark matter. Dark matter is matter that does not interact with electromagnetic radiation. It emits no light. It absorbs no light. It scatters no light. It is completely invisible across the entire electromagnetic spectrum. Direct detection of dark matter has not been achieved. We cannot see it, but we can see what it does. Dark matter has mass. Mass curves spacetime. Curved spacetime bends light. By measuring the bending of light, you can map the mass distribution that caused the bending, whether or not that mass is visible. This is how dark matter has been mapped, not from seeing it, from seeing what it does to light. The technique of weak gravitational lensing measures the slight distortion of background galaxy shapes caused by mass in the foreground. Background galaxies, which should have randomly oriented shapes on average, show a subtle, coherent alignment when their light has passed through a region of foreground mass. They are stretched slightly in the direction perpendicular to the foreground mass. The effect in any single galaxy is tiny, far smaller than the intrinsic variation in galaxy shapes. But averaged across thousands or tens of thousands of galaxies, the statistical signal emerges clearly. By measuring the pattern of these tiny distortions across large patches of sky, astronomers can reconstruct the distribution of mass in the foreground. Not just the visible mass, not just the luminous matter in stars and hot gas, total mass, including all the dark matter. The results are striking. Galaxy clusters contain roughly 6 times as much dark matter as ordinary matter. The large-scale structure of the universe, the vast cosmic web of filaments and voids and clusters, is shaped primarily by dark matter. Ordinary matter falls into the gravitational wells created by dark matter and forms galaxies and clusters. Without dark matter, the universe would look completely different. Galaxy formation would have been much slower, and galaxies would be much less massive. The cosmic web, as we observe it, would not exist. All of this determined primarily through the bending of light by gravity. The most direct piece of evidence for the separation of dark matter from ordinary matter comes from the bullet cluster. The bullet cluster is the product of a collision between 2 galaxy clusters. The collision happened roughly 150 million years ago. The 2 clusters, each containing thousands of galaxies, enormous clouds of hot gas, and vast halos of dark matter, passed through each other. During the collision, the galaxies in each cluster mostly passed through without interacting directly. Individual stars within galaxies are so widely separated that direct stellar collisions are rare, even during a full galaxy collision. The galaxies sailed through. The hot gas in each cluster did not pass through so easily. Hot gas in galaxy clusters constitutes the majority of ordinary matter in the cluster, by mass. When the 2 gas clouds collided, they slammed into each other like 2 clouds of ordinary matter. The gas was slowed by the collision, heated to even higher temperatures by the shock, and remained concentrated near the center of the collision zone. The dark matter in each cluster behaved completely differently. Dark matter does not interact electromagnetically. It passes through other dark matter with essentially no interaction. The dark matter halos from the 2 clusters pass through each other without slowing, continuing on their original trajectories. The dark matter from each cluster is now displaced from the hot gas, sitting as 2 separate concentrations on either side of the central gas cloud. Both components of this collision are visible. The hot gas glows in X-rays and was imaged by the Chandra X-ray Observatory. It appears as a bright, elongated region near the center of the system. The dark matter was mapped by weak gravitational lensing using optical observations of the distorted shapes of background galaxies behind the system. The lensing map shows 2 mass concentrations separated by millions of light-years, one on each side of the hot gas. The visible matter, the gas, is in the center. The total mass, dominated by dark matter, is separated to either side. The 2 maps, X-ray brightness and weak lensing mass, are displaced from each other, visibly, photographically, undeniably displaced. This is one of the clearest, most direct pieces of evidence for dark matter. The 2 components of the cluster, ordinary matter and dark matter, behave differently during the collision because they interact differently. Ordinary matter interacted electromagnetically and was slowed. Dark matter didn't interact and kept going. The displacement shows it directly. And the tool that revealed the dark matter distribution, the tool that made the dark matter map, was gravitational lensing, the bending of light by gravity. Massless photons from background galaxies, bent by the gravity of invisible dark matter, revealing the presence and distribution of something completely undetectable by any other means. Light made the invisible visible. The original question, how can gravity bend light if light has no mass, contains within it an assumption so deeply embedded in intuition that it took centuries to question. The assumption that gravity is a force that acts on mass. The history of physics shows that deeply embedded assumptions are often the hardest to dislodge. Newton's gravity worked so well, for so long, in so many circumstances, that questioning its conceptual foundations seemed almost unnecessary. It explained everything anyone could measure. Why look deeper? The answer came not from any failure of Newtonian gravity in its natural domain. It came from Einstein asking a different kind of question. Not what happens in a gravitational field, but what is a gravitational field? Not how does gravity affect things, but what is gravity? And the answer, once found, was so fundamentally different from what came before that it required replacing not just the equations, but the entire conceptual framework. Gravity is not a force. Gravity is geometry. Space and time are not a fixed background stage. They are a dynamic fabric that curves in response to mass and energy. Objects move along the straightest available paths through that curved fabric. Everything follows those paths, including light, including things with no mass. Because the paths are features of the fabric, not features of the objects traveling them. The path bends because the fabric bends. The object just follows. This reframing dissolved the original question. The question assumed a conceptual framework that turned out to be wrong. Once you have the right framework, the answer is obvious. Of course, light bends. Everything bends. Bending is what following curved geodesics looks like from the outside. And near massive objects, all geodesics are curved. Consider what it means that we can photograph all of this. In 1865, James Clerk Maxwell unified electricity and magnetism and predicted that light is an electromagnetic wave. In 1887, Michelson and Morley found that the speed of light is the same in all directions, a strange result with no explanation in existing physics. In 1905, Einstein explained it by replacing absolute space and time with relative space-time. In 1915, Einstein extended this to include gravity, replacing Newton's force law with the geometry of curved space-time. In 1919, Eddington measured the deflection of starlight by the sun and found it matched Einstein's prediction. In 1979, Walsh, Carswell, and Weyman discovered the first gravitational lens. In 1990, the Hubble Space Telescope was launched and began capturing images of gravitational arcs and Einstein rings in extraordinary detail. In 2015, LIGO detected gravitational waves for the first time, adding an entirely new observational channel to astronomy. In 2019, the Event Horizon Telescope photographed the shadow of the black hole in Messier 87. In 2022, it photographed Sagittarius A. From Maxwell to the black hole photographs is less than 160 years. From Newton's Principia to the photograph of Sagittarius A is less than 340 years. In the span of a few human generations, the understanding of gravity went from a force acting on mass to the geometry of space-time, and we went from being unable to test whether light bends at all to photographing the event horizon of a black hole 55 million light-years away. The pace of this understanding is almost as staggering as the physics itself. When you look up at the stars tonight, each photon reaching your eye has traveled through curved space-time, bent slightly by the gravity of every massive object it passed near on its journey, delayed slightly by every gravitational well it had to climb out of, shifted slightly in frequency by every gravitational field it traversed. The image of the universe that reaches your eye is not the flat, unmodified snapshot of a universe in flat space. It is a gravitationally distorted image, bent and shaped by the curvature of space-time along every line of sight. In deep-field photographs, galaxy clusters, surrounded by arcs of light, are showing you the shape of space-time. Those arcs are not coincidences of geometry. They are the literal traces of curved geodesics, the paths that photons followed through warped space-time. The bright ring around the shadow of Sagittarius A is the photon sphere of a black hole, made visible because photons from the surrounding accretion disk were bent so severely that they wrapped partway around the black hole before escaping toward our instruments. The slight displacement of stars during a solar eclipse is the spatial curvature of space-time near the Sun, adding its contribution to the time curvature and doubling the deflection that Newton would have predicted. Every arc, every ring, every lensed image, every GPS correction, every Shapiro delay. They are all the same thing. Space-time has shape. Light follows that shape. Not because gravity grabs it. Not because a force acts on its mass. Because the road it travels is curved. And the road is curved because the universe is filled with mass and energy. And mass and energy curve space-time. And curved space-time is what gravity actually is. The question dissolves when you have the right picture. Light has no mass. But light moves through space-time. Space-time curves near mass. And everything that moves through curved space-time follows the curves, including light. That is the answer. That is all the answer there is. Now there is another consequence of space-time curvature that deserves its own careful treatment, because it connects the purely theoretical to something you can demonstrate with a wristwatch and a tower. When light climbs out of a gravitational well, it loses energy. Not mass, since it has no mass to lose. Energy. Specifically, the frequency of the photon decreases as it climbs. The wavelength gets longer. In visible light, longer wavelength corresponds to a shift toward the red end of the spectrum. This is called gravitational redshift, and it is as real and measurable as anything in physics. Einstein predicted gravitational redshift as early as 1907, before general relativity was even complete. He derived it from the equivalence principle alone. Here is the logic. You're in a rocket, accelerating upward. Someone near the base of the rocket emits a flash of light upward. During the time the light travels from the emitter to a receiver at the top of the rocket has accelerated. The receiver is moving away from the direction the light is traveling. From the perspective of the light, the receiver has Doppler shifted. Doppler shift toward lower frequency. The receiver sees the light as redshifted relative to what the emitter sent. This is a straightforward calculation in special relativity. An accelerating receiver sees a source behind it as redshifted. By the equivalence principle, the same thing must happen in a gravitational field. Light emitted from lower in a gravitational field and received higher up should be redshifted. The photon is climbing out of the gravitational well. It loses energy. Its frequency decreases. Its wavelength increases. A shift toward the red. The converse is also true. Light falling into a gravitational well gains energy. Its frequency increases. its wavelength decreases. A shift toward the blue. Gravitational blue shift. Einstein also predicted that gravitational redshift implies gravitational time dilation. If clocks at different heights in a gravitational field are compared, they must run at different rates. Because if they didn't, you could use the rate of light emission as a clock comparison, and the gravitational redshift would violate the comparison. Clocks at lower gravitational potential, closer to the mass, run more slowly. Clocks at higher potential, farther from the mass, run faster. The rate of time passage depends on where you are in a gravitational field. This is not a metaphor. Time itself runs at different rates, at different positions in a gravitational field. The first direct laboratory confirmation of gravitational redshift came in 1959. Robert Pound and Glenn Rebka at Harvard University devised a remarkably elegant experiment. The Jefferson Physical Laboratory at Harvard has a tower 22.5 meters tall. Pound and Rebka mounted a gamma-ray source at the bottom of the tower and a gamma-ray detector at the top. The source was iron-57, an isotope of iron that, when excited, emits gamma rays at an extraordinarily precise frequency. The precision arises from a phenomenon called the Mossbauer effect, discovered the previous year by Rudolf Mossbauer. The Mossbauer effect allows gamma rays to be emitted and absorbed by nuclei with a precision of about 1 part in 10 to the power of 12. A precision so extraordinary that tiny fractional shifts in frequency are detectable. The frequency shift expected from gravitational redshift across 22.5 meters is about 2.5 times 10 to the power of -15. A shift of 2.5 parts in 1 million billion. That's an unimaginably small fractional change. Pound and Rebka measured it. They confirmed gravitational redshift to within 10% of the predicted value. Later measurements, using a refined version of the experiment, confirmed the prediction to within 1%. The gravitational redshift was real, confirmed directly in a laboratory. Across a tower 22.5 meters tall. The effect was too small to have any practical consequence for everyday physics, but it confirmed the essential correctness of Einstein's picture of curved spacetime and its effect on the propagation of light. Since then, gravitational redshift has been measured in many other systems. White dwarf stars produce measurable gravitational redshift. White dwarfs are the remnants of stars similar to the Sun, but compressed into a sphere roughly the size of Earth. Their surface gravity is roughly 10,000 times stronger than Earth's. Light emitted from the surface of a white dwarf is measurably redshifted by the time it reaches Earth. The redshift can be measured spectroscopically by comparing the wavelengths of spectral lines from the white dwarf to the known wavelengths of the same lines in a laboratory. White dwarf redshifts confirm gravitational redshift for much stronger gravitational fields than a laboratory tower can provide. Neutron stars provide an even more extreme test. A neutron star packs roughly 1.5 to 2 times the mass of the Sun into a sphere about 20 kilometers across. The surface gravity is about 100 billion times stronger than Earth's. Light from a neutron star's surface is severely redshifted by the time it reaches a distant observer. Measurements of neutron star spectra confirm gravitational redshift under conditions vastly more extreme than anything in the solar system. And for the most extreme objects, black holes, the redshift becomes infinite at the event horizon. Light emitted just above the event horizon arrives at a distant observer at a frequency tending towards 0. The light has lost essentially all its energy, climbing out of the deepest gravitational well in nature. Gravitational redshift connects directly to the twin paradox of general relativity, not the special relativistic twin paradox, which involves motion, the gravitational version. If one twin spends years living at a lower altitude, near sea level, while the other spends years at a higher altitude, say near the top of a mountain, when they reunite, the twin, who lived at lower altitude, will have aged slightly less. Their clock, their biological processes, ran slightly more slowly in the stronger gravitational field. The effect is tiny at human scales, but it is real. GPS confirms it every day. The altitude difference between the GPS satellites and Earth's surface causes the satellite clocks to tick faster than ground clocks. You cannot separate the bending of light by gravity from the slowing of time by gravity. They are two aspects of the same underlying reality, the geometry of space-time. There is also the question of pulsars and what they have taught us about the bending of light and the warping of space-time. Pulsars are rapidly rotating neutron stars that emit beams of radio waves from their magnetic poles. As the neutron star rotates, the beam sweeps across the sky like a lighthouse beam. If Earth happens to lie in the path of the beam, we receive regular pulses of radio waves. The timing of these pulses is extraordinarily precise. The most stable pulsars are more accurate timekeepers than any atomic clock on Earth. They are used as precision measuring instruments to test general relativity in ways that no other system can. In 1974, Russell Hulse and Joseph Taylor discovered a pulsar orbiting another neutron star, a binary pulsar system. As the two neutron stars orbit each other, their orbital parameters change slowly over time. The orbital period decreases gradually, meaning the stars are slowly spiraling toward each other. The rate at which the orbital period decreases can be calculated from general relativity. According to general relativity, the spiraling in is caused by the emission of gravitational waves. The two neutron stars, orbiting each other at a significant fraction of the speed of light, are constantly generating gravitational waves, ripples in space-time, and these waves carry away orbital energy. As energy is lost, the orbit shrinks. The orbital period decreases at a calculable rate. Hulse and Taylor measured the rate. It matched the prediction of general relativity to within fractions of a percent. For the first time, there was indirect evidence that gravitational waves are real. Hulse and Taylor were awarded the Nobel Prize in Physics in 1993 for this discovery. The binary pulsar system also shows another effect relevant to the bending of light. As the pulsing radio signals from the active pulsar travel toward Earth, they pass near or through the gravitational field of the companion neutron star at different points in the orbit. When the geometry is right, the signals pass close to the companion and experience a Shapiro delay, arriving slightly later than they would if the companion weren't there. This effect has been measured in several binary pulsar systems. The measurements match the predictions of general relativity. Another confirmation, in a completely different regime from solar system tests: strong gravitational fields, relativistic orbital speeds, compact objects. Everything agrees with the same theory. The connection between the bending of light and the larger structure of the universe deserves explicit attention, because the two are linked through dark energy as well as dark matter. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate. In 1998, two independent teams studying distant Type Ia supernovae made a surprising discovery. Type Ia supernovae are standardizable candles. They all have approximately the same intrinsic brightness when properly calibrated. By measuring their apparent brightness, you can calculate their distance. By measuring their redshift, you know their recession velocity. The two teams, one led by Saul Perlmutter and one by Brian Schmidt and Adam Rees, expected to find that the expansion of the universe was slowing down. The gravitational attraction of all the matter in the universe should decelerate the expansion. The distant supernovae should be slightly brighter than a model with no deceleration would predict, because they're slightly closer than simple Hubble flow would place them. Instead, they found the opposite. The distant supernovae were dimmer than expected, farther away than expected. The expansion of the universe was not decelerating. It was accelerating. Something was driving the universe to expand faster and faster. That something has been called dark energy. It makes up about 68% of the total energy content of the universe. It pervades all of space uniformly. It has negative pressure, which, in the context of general relativity, means it acts as an accelerating agent for cosmic expansion rather than a decelerating one. Its nature is unknown. The leading candidate is the cosmological constant, a term Einstein actually introduced into his field equations in 1917 and then removed in 1930 when Edwin Hubble showed the universe was expanding. Einstein called removing it his greatest blunder. But if the cosmological constant represents the energy density of the vacuum itself, a quantum mechanical effect, it might explain dark energy. The problem is that when physicists calculate the energy density of the quantum vacuum from quantum field theory, the answer is about 10 to the power of 120 times larger than what we observe. That is one of the largest discrepancies between theory and observation in all of physics. What dark energy is, precisely, we don't know. But we know it's there. And gravitational lensing is one of the tools used to constrain its properties. Large-scale, weak lensing surveys measure the distribution of dark matter and ordinary matter across billions of light-years and across cosmic time. By comparing how the matter distribution has changed over cosmic history, astronomers can determine how the universe's expansion has evolved, which in turn constrains the properties of dark energy. If dark energy is a cosmological constant, the lensing surveys should see a specific pattern of growth in large-scale structure over time. If dark energy evolves with time, the pattern would be different. Current surveys, including the Dark Energy Survey and the Kilo Degree Survey, have measured weak lensing signals from hundreds of millions of galaxies. The results are consistent with the standard cosmological model, which includes both dark matter and dark energy. Future surveys, particularly the Euclid satellite, launched in 2023, and the Vera-C, Rubin Observatory, beginning operations in the mid-2020s, will map weak lensing across enormous volumes of the universe. They will constrain the properties of dark energy far more precisely than current surveys. And their primary tool will be gravitational lensing, the bending of light by gravity. Massless photons, tracing the geometry of space-time, revealing the composition and history of the universe. It is a remarkable circle. The question of why gravity bends light leads to the discovery that gravity is space-time geometry. And space-time geometry, as a tool applied to the whole universe, reveals the composition of the cosmos. Dark matter. dark energy. The large-scale structure, the history of cosmic expansion, all of it legible through the bending of light. There is one more perspective worth bringing to this, because it touches on what makes physics different from merely cataloguing observations. Physics aims not just to describe what happens, but to understand why. And general relativity is perhaps the most striking example in all of science of a theory where the why is completely clear. Once you have the right framework. In Newton's theory, the bending of light by gravity would have been inexplicable. There is no mechanism in Newtonian gravity for a force proportional to mass to act on something with no mass. The question has no answer in that framework. The observation, if confirmed, would have been a mystery, an anomaly demanding explanation. In general relativity, the bending of light is not an anomaly. It is a theorem. It follows, inevitably, from the postulates of the theory. If gravity is the curvature of space-time, and if objects follow geodesics through curved space-time, and if light is a form of electromagnetic energy that propagates through space-time, then light must follow geodesics. And geodesics in curved space-time are curved. Therefore, light bends in gravitational fields. The proof is trivially short. The hard part was figuring out what gravity actually is. Once you have that, everything else follows. This is the hallmark of a deep physical theory. It doesn't just match observations. It makes observations inevitable. It makes the universe behave the way it does for reasons that can be stated clearly and followed from a small number of fundamental principles. Newtonian gravity was a deep theory in its time. It reduced a vast range of phenomena to a single equation. But it didn't explain why masses attract. It described the fact without providing any underlying mechanism. Newton himself was aware of this limitation. He famously wrote in the Principia that he had been unable to discover the cause of those properties of gravity from phenomena, and he would not pretend to know it. Hypotheses non fingo. I feign no hypotheses. He described what gravity does without claiming to know what gravity is. Einstein's general relativity answered that question. Gravity is the curvature of space-time. Masses attract because mass curves space-time and everything follows the geodesics of curved space-time. Light bends because geodesics in curved space-time are curved. Clocks run slow near masses because time itself is part of the curved space-time fabric. GPS needs relativistic corrections because time dilation near Earth's mass is real. Gravitational waves are real because space-time is a dynamic fabric that can ripple. Black holes are real because space-time can curve so severely that all geodesics lead inward. All of this follows from one principle. Gravity is geometry. It is a principle of astonishing explanatory power. It explains not just one thing, but everything. Not just qualitatively, but quantitatively, with extraordinary precision across a vast range of scales and conditions. From the deflection of starlight by the sun, to the inspiral of binary neutron stars, to the shadow of a black hole 55 million light-years away. Everything matches. Everything confirms the same picture. The geometry of space-time is real, and light traces it. You might think about this the next time you look at the night sky. Every photon reaching your eye has traveled through curved space-time, bent by galaxies along the way, delayed by gravitational wells it had to climb out of, shifted in frequency by every gravitational field it traversed. The image of the universe you see is a gravitationally lensed image. It is not what the universe would look like if space-time were flat. It is what the universe looks like through the lens of its own gravity. And it is only because we understand general relativity that we know how to account for those distortions, how to remove them to see the underlying structure, how to use them as signals of invisible mass, how to turn a fundamental feature of the universe into an astronomical tool. This is what physics, at its best, looks like. A question that initially seems paradoxical, how can gravity bend something with no mass, leads to a complete reconstruction of what gravity is, which leads to a tool for studying the universe that would have seemed like magic to Newton, which leads to discoveries about dark matter and dark energy and the expansion history of the cosmos. One question, followed honestly, leads all the way to the composition of the universe. The fact that this chain of reasoning started with Einstein sitting at his desk in a patent office in Bern, doing physics in his spare time, with no laboratory and no students and no institutional resources, is a reminder of what is possible when someone asks the right question and follows it without flinching. Einstein asked what gravity actually is. Not just how it behaves, what it is. And the answer was this: gravity is the shape of space-time. Light follows that shape, not because gravity acts on it, because the shape is what everything follows. And every time a telescope photographs a gravitational arc, every time GPS corrects for relativistic time dilation, every time astronomers map dark matter through the distorted shapes of background galaxies, every time the Event Horizon Telescope images a black hole's shadow, this answer is confirmed again. The universe is built from geometry, all the way down, and light, massless and swift, traces it for us. There is also something that happens at the boundary between quantum mechanics and general relativity that is subtle but worth understanding, because it reshapes what we mean when we say light follows curved space-time. In quantum mechanics, a photon does not have a definite trajectory. It has a probability amplitude for different trajectories. When Richard Feynman developed his path integral formulation of quantum mechanics in the 1940s, he showed that a particle traveling between 2 points takes all possible paths simultaneously, in a quantum sense. The classical path, the one described by geodesics in general relativity, is the path that has the highest probability amplitude, the path around which quantum fluctuations mostly cancel. For massive particles in flat space-time, this is the straight-line path. For photons in curved space-time, the highest probability path is the geodesic, through the curved space. In the semi-classical approximation, where quantum effects are small and space-time curvature is treated classically, the photon follows its geodesic just as general relativity says. The geodesic description is accurate. But strictly speaking, the photon takes all possible paths. The geodesic is just the most probable one. And in regimes where quantum effects are large, near the Planck scale, this distinction matters enormously. Quantum fluctuations in the metric itself, in the geometry of space-time, would cause photons to scatter off the fluctuating geometry. The geodesic picture would break down. Space-time would no longer be a smooth background through which photons propagate. It would itself be a quantum system, fluctuating, foamy, uncertain. This is the regime of quantum gravity, and we cannot yet calculate what happens to light in that regime. The mathematics of quantum gravity is not controlled. We don't have a perturbation theory that reliably describes quantum corrections to general relativistic photon propagation near the Planck scale. String theory has proposals. Loop quantum gravity has proposals. But neither has been shown to give a complete, consistent, testable picture. So the statement that light follows geodesics is accurate in every regime we have access to. But it may not be the final word. At the deepest level, the nature of light's propagation through curved spacetime may look different in a full theory of quantum gravity. This is not a weakness of general relativity. It is an honest acknowledgement of its domain of applicability. General relativity is one of the most successful physical theories ever constructed. It is valid over an extraordinary range of scales and conditions. But the universe has regimes it doesn't reach. And in those regimes, the story of how gravity bends light is likely more subtle than what we've described here. We don't know the details, yet. That is the frontier. And frontiers, in physics as elsewhere, are where the most interesting things happen. The story of gravitational lensing has a chapter that connects to the very largest structures in the universe, and it is worth telling. The cosmic microwave background is the oldest light in the universe. It was emitted when the universe was about 380,000 years old, when it had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, the universe was a hot, dense plasma, opaque to radiation. Photons scattered constantly off free electrons, unable to travel more than a short distance. When the electrons combined with protons to form neutral atoms, the universe became transparent. The photons streamed freely for the first time. They have been traveling ever since. 14 billion years. They are still traveling today. They fill the entire universe uniformly, reaching us from every direction with a temperature of about 2.73 Kelvin, just above absolute zero. This is the cosmic microwave background. It was discovered in 1964 by Arno Penzias and Robert Wilson at Bell Telephone Laboratories, who detected it as an unexplained uniform noise in their radio antenna. They were awarded the Nobel Prize for the discovery in 1978. The cosmic microwave background is extraordinarily uniform, but it is not perfectly uniform. It has tiny temperature fluctuations at the level of about 1 part in 100,000. These fluctuations represent slight overdensities and underdensities in the matter distribution of the early universe. Regions that were slightly denser attracted more matter gravitationally. Over billions of years, those overdense regions grew into galaxies and galaxy clusters. The underdense regions became the vast cosmic voids. The cosmic microwave background is a snapshot of the seeds from which all of cosmic structure grew. And because the cosmic microwave background has traveled through the entire observable universe to reach us, it has passed through the gravitational fields of every large-scale structure along the way. Every galaxy cluster, every filament, every cosmic web structure has slightly lensed the cosmic microwave background light. The lensing is subtle. The temperature fluctuations in the cosmic microwave background are already tiny. The additional distortions from lensing are even tinier. But they are measurable. And measuring them tells you about all the mass along the line of sight between us and the last scattering surface, where the cosmic microwave background photons were last scattered before streaming freely. This technique, called CMB lensing, has become one of the most powerful tools in cosmology. By measuring how the cosmic microwave background is lensed, scientists can reconstruct the distribution of all matter, dark and luminous. along every line of sight across the entire observable universe. The Planck satellite, which measured the cosmic microwave background with extraordinary precision from 2009 to 2013, detected CMB lensing clearly. It measured the matter distribution across billions of light-years of cosmic history. The results are consistent with the standard cosmological model. The Atacama Cosmology Telescope and the South Pole Telescope have made even more precise measurements of CMB lensing. Future experiments, including the Simons Observatory, the CMB-S4 experiment, and the Lightbird satellite, will push this precision much further. They will constrain the sum of neutrino masses, which affects how structure forms and is imprinted in the CMB lensing signal. They will constrain the properties of dark energy. They will test whether the standard cosmological model continues to hold at increasingly precise levels. All of this from the bending of light by gravity. The oldest light in the universe, lensed by 4 billion years of accumulated cosmic structure, revealing the composition and evolution of everything. Now, come back to Earth for a moment, and to something more immediate. General relativity predicts that time runs at different rates in different gravitational potentials. Clocks at lower gravitational potential, closer to the Earth, run more slowly than clocks at higher potential. This effect is precisely measurable with atomic clocks. In 1971, Joseph Hafele and Richard Keating flew atomic clocks on commercial airliners around the world. They compared the airborne clocks to reference clocks left on the ground. The airborne clocks experienced both effects. They were at higher altitude, so they ran faster due to weaker gravity. They were moving, so they ran slower due to velocity-time dilation. The net effects were predicted by general relativity and special relativity combined. When the clocks returned, they matched the predictions. The gravitational effect was real. The velocity effect was real. Both effects combined to produce the predicted net time difference. The differences were small, hundreds of nanoseconds, but they were real, and they matched the predictions. This was one of the first direct experimental confirmations of both gravitational time dilation and velocity time dilation in an everyday technological setting. Since then, more precise tests have been done. Atomic clocks have been flown on aircraft and rockets. Clocks have been compared between different altitudes on Earth. The ACES experiment, the Atomic Clock Ensemble in space, has compared clocks on the International Space Station to ground clocks with extraordinary precision. Every measurement confirms the predictions. Time runs at different rates in different gravitational potentials. It runs faster, higher up. It runs slower, lower down. And this effect, applied to GPS satellites at 20,000 kilometers altitude, requires the 38 microsecond per day correction to keep the system accurate. The geometry of space-time is not theoretical. It is engineered into the systems that modern civilization depends upon. Every time, physics has asked, what is the deeper reason behind an observed phenomenon? The answer has expanded our understanding of reality. Newton asked why objects fall and why planets orbit. The answer was gravity, a force proportional to mass. It explained everything observable. But it left a question: what is gravity? Einstein answered, gravity is the curvature of space-time. The answer explained not just why objects fall and planets orbit, but why time runs slow near masses, why light bends, why gravitational waves exist, why black holes have event horizons. It unified all of these under a single geometric principle. Now physicists are asking, what is space-time? What is the deep structure of the curved fabric that gravity is the geometry of? String theory answers that space-time emerges from the dynamics of fundamental strings. Loop quantum gravity answers that space-time is made of discrete quanta of geometry, like pixels of space. Other approaches have other answers. We don't know which, if any, is right. We don't have a quantum theory of gravity, but we know the question. And having the question clearly stated, with general relativity as the framework it must reduce to in the classical limit, is enormous progress. One day, the answer will come, and it will likely reveal something about light propagation, about black holes, about the very early universe that we cannot currently anticipate. Just as Einstein's answer revealed the gravitational lensing and the GPS corrections and the black hole shadows that Newton's theory could never have predicted. The universe is consistently more interesting than our best theories expect. And the bending of light by gravity is, in many ways, where that pattern of discovery began. Good night.